Okay.
Sure, happy to say something at the outset. Maria has taken on an open problem that we are incredibly interested in and has been fantastic at exploring the viable options to answer that question. She is definitely at the border of what we know and the known unknowns of the project space. We have some awesome collaborators in the Chaos Foundation, which we'll describe later, that have helped illuminate the path, but really Maria's been driving this the whole way. So with all of that being said, it's been awesome to work with her, and we're incredibly excited to have her with our team for this summer as well. So not much more needs to be said about her.
All right, well, I don't know if I can top that, but with all that being said, I think this is a good point to start off the presentation. I just want to thank you all for coming. I know it's a lovely day outside, and I'm glad you guys chose to be here and not out there with all the sun. And I just wanted to add, it's been an absolute pleasure working with the Red Hat Collaboratory program through Boston University. It has definitely given me so much experience and just been a joy to work with. And I'm really excited to share all my work with you today. I hope you find this insightful. And let's start with the research. So in today's presentation, I will be sharing my work from this past semester that I completed in collaboration with Project Aspen, formerly known as Project San Diego, which is a project within the Red Hat Open Source Programs Office. My research was largely focused around evaluating the health and growth of open source communities in a way that can help provide community managers with data-driven insights into their projects. And James, who just gave me a lovely introduction, I've had the pleasure of having him as my mentor throughout this project. He has been nothing short of extremely helpful throughout each and every step of this project, so wouldn't have asked for anyone else to have as a mentor. Thank you, James. All right, so just to give you all a quick idea of what to expect in this presentation, I will start off with some introductions. Who am I? What is Project Aspen? What is Augur? And then that will bring us to the research question itself, which we'll discuss, and we'll talk about the methodology and the results and limitations behind our unsupervised community clustering approach, which will then lead us to phase 2 of the research, where we explore contributor social networks and open source communities. We'll talk about some key definitions and the 2 approaches that we used, which were the count-based and the network-based approaches. And then we'll look at how contributors behave and grow over time in open source projects. And lastly, some key takeaways and what to expect next from all of this research. All right, so a little bit about me. I am a very recent Boston University graduate. I graduated about 2 weeks ago. It's actually one day before coming straight back as a summer intern at Red Hat. I graduated with degrees in biomedical engineering and computer science, and I will be going straight back in the fall to pursue a master's in artificial intelligence. So hopefully you guys can keep my seat warm for when I'm done with that. I'm no stranger to Red Hat, as some of you may know. I started my journey back in the fall of 2021 with the VU Collaboratory program, where I was working with Lance Galletti on adversarial machine learning research. After that, I joined as an intern for summer of 2022, working with the Red Hat OpenShift data science team as a software engineering intern. And that brought me right back to VU Collaboratory for this past year, where I worked with OSPO on this project, and back yet again for the summer, again with OSPO as a data science intern, with hopefully more to come to that list. Some very brief background. I was born and raised in Moscow in Russia. I played water polo throughout college, which was super fun, and I love very stereotypically grandma hobbies like crocheting little animals. And yeah, proud mother of 2 kids, and that's not all you need to know. All right, so what is Project Aspen? This research that I'm presenting today is my contribution to the project, and Aspen is comprised of 2 main components. So 8Knot is a dashboard application that utilizes the Augur database to provide users and community managers with data-driven insights into their GitHub projects. The second component, Repel, focuses on mainly the research behind the application, with the current focus on developer social network analysis of open source projects, which is specifically what I have been working on throughout this past semester. Augur is the open source database that basically makes all of this research and Project Aspen as a whole possible. They provide us with mountains of structured, validated data for open source software projects on GitHub, and it's an incredible tool that has been 6 years in the making. So they really know what they're doing. So Augur gives us the data, and having data, that's a great thing, but it's not necessarily useful if you can't draw any information from it, which is exactly what 8not does by analyzing and visualizing the data provided to us by Augur. So what has been my contribution? My initial idea for evaluating a project was to take the relative route. So looking at its health from the standpoint of what do the neighbors of that project look like and how are they behaving. So the question I posed was are projects of similar health and maturity stages close together in a naive embedding? Meaning, can we evaluate a project based on its neighbors? So the first experiment was born where we applied a community clustering approach, which is unsupervised, to the Augur data available to us. Intuitively, we made some assumptions. We assumed that projects at a similar health level and stages of maturity should be close to each other, as well as neighbors of known successful projects must also be successful. So think of ecosystem rock stars like Kubernetes, for example. Following initial feature engineering, our strategy was basically to identify any important features that might be helpful in the clustering process, as well as the optimal number of clusters. This would then give us the basic foundation for creating high dimensionality embedding and running our unsupervised clustering algorithm on the data. After that, we use dimensionality reduction techniques such as principal component analysis and singular value decomposition, which allows for better visualization and further analysis of the data. And lastly, all that was left to do was to analyze the cluster statistics that we received from the algorithm and look for patterns, see if this is actually a feasible solution to the problem. We also optimize our model by modifying the feature set and the number of clusters in order to achieve the highest possible explained variance. Right, so let's take a look at what some of those techniques look like. We use two main methods to evaluate and identify important features, starting off with a simple correlation heat map, which you can see on the left. This basically tells us the level of correlation between individual features. So for example, we can see that stars, forks, and watchers tend to be very highly correlated. However, those features also do tend to provide very little insight, so I ended up not using them at all. But that's a good thing to look at to kind of get an understanding of what's happening in that graph. And then our second technique on the right was to evaluate the magnitude of each feature value, which provided insight into how much the features at each principal component influence the clustering. So for example, here you can see that the number of commits at PC3 and the time since last update at PC2 were highly influential. And this is the type of information that we would be using later to guide our feature selection and optimize the model further. So we also had two options for approaches of identifying optimal number of clusters. The first being a little more intuitive, and that would involve utilizing a node system for categorizing a project lifestyle and the stages of it. So the example we are using here is the Apache Software Foundation. They highlight 4 stages. We have, however, made quite a few assumptions throughout this project, and there's a lot of intuition already being involved in this. So we decided to go with a little more of a computational approach where we're evaluating the information criterion to evaluate the performance of the Gaussian mixture model. So here we just look at the elbow and identify the number that is most optimal, and the lower the value, that means the better the model is. So we ended up going, I believe we did a few runs with 5, a few runs with 6, and then, optimizing from there on. Oh, here are some of the results. The resulting clusters did a phenomenal job at identifying outliers. As you can see here, known successful projects are so vastly different from the rest of the project population that they practically have their own clusters. This does, however, mean that the clusters that contain your average open source projects and they're very densely populated, they're very hard to distinguish between, and we don't really gain much insight into their stage of maturity, their health level, or any of the above. Since the distinction between them and the ecosystem rock stars like here you can see Node and Kubernetes is just so drastically different. So there were a couple of limitations that resulted in this kind of result. The short answer to the feasibility question of this approach is no, this is not the best or a feasible really solution to this problem at all. Limited cluster interpretability is one of the biggest issues here. Even if we could optimize the clustering to reach, say, 100% explained variance, we still would not know what the clusters actually mean. We would just have very defined clusters. This can be explained by the fact that open source communities simply do not behave in the same way. They're not emergent from the same distribution of behavior from the organizational standpoint and just behavioral standpoint as collaborators in general. We're also using first order statistics here. So that inherently is very limiting and sheds a lot of utility. We're not able to look at any sequential information, any temporal information, or periodical information, so evaluating the contributions over time. And lastly, project lifespan also plays a huge role here, since long-standing projects, even if they're not necessarily successful, it's not realistic to compare them with newer ones because you have such a lower values for all of the data metrics, really, like commits or issues open, issues closed. Like it's just way too distinctive to be able to make a to assign any kind of property or value to it. Oh, had a couple issues, and although this is not exactly an approach we can use in future work, we have learned a lot from this. So the question now is, how can we take a smaller but perhaps more informative bite of the problem to avoid the ambiguity and the generalization that has become an issue in this approach? So in this section, I will address a new research question, which is how can we, or can we at all, proxy community health by tracking the contributor interactions by looking at social networks. So this is kind of phase 2 of the project. First, let me introduce some of the key definitions that were outlined in literature. There are two main types of contributors that we are looking to identify and differentiate from. So we have core and peripheral contributors. Core contributors play an essential role in developing system architecture and forming the general leadership structure. They typically have more substantial long-term involvement. So think of roles like senior software engineers, community managers, or project leads. Those would be the core contributors. And then the peripheral contributors are basically everyone else. They are typically involved in bug fixes, smaller enhancements, and have more irregular short-term involvement. So the question rises of where do we draw the line between core and peripheral contributors? So literature does demonstrate that this data typically follows a zip distribution, which basically just means that the top 20 contributors, which we will call core in this case, are responsible for the vast majority, or 80% of contributions. And what we expect to see here for core contributors is that they will have greater network centrality, which we'll discuss what that means later, and more frequent and consistent contributions. So the first approach we explored to identify core contributors is based on simple count-based operationalizations. This begins with a query to collect all the desired data, which is followed by counting all individual contributors' contributions and obtaining a percentage of each type for each individual contributor. And lastly, we apply SUD-SIMP contribution distribution to obtain a sorted list of core contributors based on both the count and the percentage. There are some great things about this approach. For example, it is extremely simple and the computational cost is very low. It also allows us to apply the zip distribution since the data we're working with here is just simple counts. There are, however, a few downsides as we limit ourselves to any relational or temporal insights. So for example, if you're looking at lines of code, a contributor who made 2 very large commits would be weighed the same as someone who made 50 commits, but say with very few modifications. And that's just not exactly what we're trying to look for at this typical work. So this approach also does not consider plots, which was something that was highlighted by one of our colleagues at Google. This is a known anti-pattern, and it becomes a big issue since a lot of the individual accounts oftentimes will operate as plots, and that again acts as a limitation in this case. And we face a similar issue as we did with our clustering approach, since using first-order statistics does not really allow us to consider any things like time period, contribution consistency, any of the relational or time-based data or insights. And lastly, the result is just a list. It's going to be a list of core contributors, and that limits us to having any visualizations or graphically representing that information. So how can we do this better? We can use a network-based approach that will allow us to visualize these interactions between different contributors. Similar work has been done by our colleagues in emerging technologies, where they use a network-based approach to basically explore connections between open source projects. So in their work, their focus was on contributor interactions of different projects, while we will focus on evaluating a single project and their contributors instead. And then the paper by Mitchell Joblin that a lot of this research has been inspired by, that's where we got our definitions as well. They also highlight the promise of the network-based approach in identifying core contributors. However, when that paper was written, Augur was not yet a thing, so now we have a lot more data to work with, and it's a lot more promising now than it was back in 2016. So for our experiment, we have identified 4 main interactions that we want to evaluate. These include things like pull request reviews, commit authors, and interactions in both PR and issue message threads. So we can take a look at what some of those networks look like. For the purposes of this experiment, we have been working with the Ansible repository, and this is what the commit author network looks like. This is by far the most dense network of the 4, which is mostly due to the fact that commits are exclusively done on GitHub, while many of the issue and pull request tracking, that's been moved to Jira. So there's a lot of data missing from the Augur database simply because it's not stored on GitHub. This also explains the periods of missing data, which that's just an unrelated limitation to this project. But the distribution here is still extremely insightful. On the right, you can see the distribution of the nodes based on their weighted degree within the network, and I'll explain again what that means a little later. But it's important to note that the distribution is very highly concentrated in the very low degree measure, which demonstrates that there is a lot more peripheral nodes or contributors than there are core nodes. And there's very few outliers in our case, which you can see up top, and those are the core contributors. This type of pattern is indicative of a scale-free network, and that remains consistent pretty much through all of the other networks that we'll look at. So for example, here, you can see a similar but slightly more evenly distribution for the issue message network, and pretty much the same thing for pull requests. They are smaller, but as I said, that is mainly due to them not being hosted on GitHub, especially in recent years. There's data missing in specific periods after like 2015 or so. And then lastly, the PR review network is much smaller than the rest. This is mostly due to the fact that reviewer is typically a very high position in a community, so it's less frequent as an action for a contributor to do, and that explains the lower node density in this network. So that kind of gives you a brief idea of what the separate networks look like, and now we can take a look at them all together in a combined graph like this. We do still see the same distribution we discussed before, with a very high concentration on the perimeter of the network, which is populated by peripheral nodes of the project. And while this is a very, very satisfying image, we can make it even better by putting some more information into it. Thus far, we have been treating the interactions as all having the same relative value and using a percentage-based threshold to identify core contributors, but we can improve on that. To add even more insight into the network, we can adjust the weights of contributors, which is what basically affects the thickness of the edges between different nodes. And our intuition for assigning these weights was based on the orbit model. And the resulting weights here are 2 points for a PR review, 1 point for commit author, and then 0.5 and 0.1 for PR message threads and issue message threads for collaboration, respectively. And this way, weights are increased not only based on how many there are or the frequency of the interactions, it's also based on the significance or like relative significance of the event. As for centrality, this centrality is basically a measure of the influence of a node in a network, which we will use to identify who these core contributors are. There are several types of centrality. They're listed here, such as page rank, degree centrality, betweenness, closeness centrality. But they essentially perform the same organization. They just prioritize different factors. So we kind of have to select one here to work with. So in order to do that and select the best type of centrality for our purposes of our network, we identified the top 20 contributors for each of the centrality types, and we use those for comparison. And you can see here we found that the resulting lists of core contributors contain practically the identical contributor IDs, and they have very similar relative scores and relative score distributions. So we ended up selecting PageRank for primarily the reason that that's what our colleagues in emerging technologies use, and it is proven to work really well. And again, they all pretty much contain the same list of contributors, so there wasn't much negotiating to do there. So now, instead of using a percentage-based approach for identifying core contributors, we will be able to evaluate distribution of all node PageRank scores in a given network and use the elbow as a threshold. So you can see that here. And after looking at the distribution here, we can see that the elbow was around 0.01, which is what was selected as our core contributor threshold. Now, putting all of this together, the new interaction type weights and threshold, we get this network. Beautiful than the last. This is exactly what we want and what we expected to see. This is distribution that is indicative of a scale-free network. And for just some background, a scale-free network is one in which the distribution of links to nodes follow the power law, meaning that the vast majority of nodes have very few connections, so the peripheral nodes, while a few very important nodes, or in our case, core contributors, have huge numbers of connections, which is exactly what you see here. So this is great, but Ansible is known to be successful, and we need to evaluate whether other smaller projects follow the same distribution as a proof of concept. And that is exactly what we did here with our project that we all know and love, Augur. So we see here a very similar distribution with a slightly lower density, or I guess significantly lower density on the perimeter of the network, which simply indicates that there aren't as many peripheral contributors. And that can be explained by the fact that Augur is not only not as well known, but it also has yet to attract more interest from outside developers. And that basically indicates that everyone who's currently working on Augur is either already a part of the team or is like seriously invested in contributing to Augur, which is exactly what you would expect to see for a project at that stage. However, we do want to evaluate how true that is. So perhaps if we look at what Ansible looked like at its early stages of development, we can see a similar distribution to what we see here with Augur. So let's look at Ansible back in 2012. There it is. In this animation, we are in the core contributors in red, same as earlier on, and then the peripheral contributors are in blue. And then here, the yellow dots represent all of the new contributors that join in the given year. We can see that at early stages of development, Ansible gained a ton of peripheral contributors, which is exactly what Augur is missing. However, as it continues to grow, it's about to get to 2020, we're seeing more new contributors in the central locations. And these could be new community managers or experts that Ansible may have hired to help with the growth of, or just like Ansible in the industry at later stages in development. So this is really interesting to see, and you really get an idea of what a project's life cycle looks like through a social network. So what have we learned from all of this? First off, networks are an incredibly insightful way to track the growth of a project by looking within at the interactions and the behavior of its contributors. Unlike with the count-based approach, networks allow us to perform periodical analysis and actually visualize the interactions. We can also perform structural equivalence analysis that will help us identify which contributors tend to collaborate with each other, or maybe which contributors have expertise in the same or similar areas, and that can help guide organizational changes within the project. But this is only the tip of the iceberg, since there's so much more we can do with this. Firstly, we can analyze interactions between different contributors and different contributor types to see whether core peripheral block model follows the desired structure outline in literature. And ideally, what we would want to see here is more frequent interactions within or among core contributors, and then less frequent interactions between peripheral. And then another thing to explore here would be time decay. So by applying a decay factor to older events in the stream, we can prioritize and give more weight to more recent events. So we can learn, or what have we learned from developer social network analysis, and where can this go in the future? The first thing we learned was that relatively mature projects, such as Ansible, in this case, they're being actively governed, may have a large core group and a much larger peripheral contributor group. So following the distribution that we were looking at earlier. This, again, is the behavior that we want to see in a scale-free network, where your core group is significantly more concentrated with contributions than your peripheral group. And this basically just means that there is a lot of outside interest in the project, and that the peripheral contributors often are fed into the core group, while more interest is being added to the outskirts of the network, so the peripheral group. The other thing that we learned with Augur here is that projects like Augur may have a large population of core contributors, but relatively few peripheral contributors. This means that the projects like Augur that are more nascent are not a scale-free network, and don't follow the scale-free distribution, which is indicative of a lower interest, outside interest in the project, but a very concentrated contribution from within the project itself. And this basically implies that the structure of the developer social network may be a candidate proxy for project development stage and overall health. So I do think this work, and this specifically the social network analysis, can really be helpful in evaluating not only project health, but also project stages of maturity, and evaluating the behavior over time of any given project, given what we know now. And by evaluating projects like Ansible and looking into Kubernetes and Node and other successful known ecosystem rock stars, we can see what a successful project like that looks like, and use that to map the expected or desired behavior for a project that is whose goal is to grow and gain more, I guess, peripheral contributors, so gain more outside contribution. And that is it for me. So I will gladly take any questions you may have. I'm sorry I went a little over time. So anyone who was able to stay, I would love to chat about this.
Was there anything that you guys were able to find about qualitatively about the code change requests? So, for example, we try to move towards many smaller changes as opposed to large ones. I was just curious if there was any qualitative evaluation you guys were able to make of that.
Is this referring back to the clustering mechanism? So no, I want to say no. We purely just use the features for the clustering itself, so for the unsupervised algorithm. So no, we didn't end up looking kind of deeper into that. But the count-based optimizations for the looking at contributor relationships, they do, at least that paper that we looked at does outline lines of code as a significant like metric to look at when evaluating for core contributors. So yeah.
Cool.
Yeah. Thank you.
Did you look at well, you must have looked at some projects that failed, right? But you don't have examples of them here. Is that because it was too hard to come up with analysis of things that failed, or?
When are you referring project that failed, like open source projects that weren't successful, or
that would be called not healthy by whatever criteria you have?
That's a great question. So no, that's a great thing to look into, actually. So I will definitely put that on the next to-do list of a network that, you know, shows you what not to do. So yeah, thank you for that. That's a great suggestion.
Oh, you have to be careful who you pick, though.
Don't want to be too offensive, but yeah. Hi, James.
Yeah, I'm so sorry to jump in on that one, but it is important to bring up that we definitely focus more on positive signal than we should. What Maria's work shows is that there is an indication that in the positive signal, we can find growth in the direction of maturity. But a next step will be, does this generalize to the case where a project is on the track towards retirement or something like that? So we have good ground truth vectors for that coming from software foundations. Like the Apache Software Foundation has specific categories of projects that have entered the retired domain. So that's like an apolitical thing to say, okay, what did the, and this is an area for further inquiry, which to me would be a guess of like, over time, does the number of core contributors decrease as we get to the retirement threshold? Do the number of peripheral contributors decrease? Because in the end, what we want to do is create a more general model that says, as a project evolves, how do the concentrations of contributors flow, and how does the real number of these people in these roles change? So, sorry, just wanted to really address that because it is a very interesting question and something that deserves inspection.
Definitely. We also do have a project in the works that focuses more on the clustering approach that we addressed earlier in the presentation. But this time, what we're trying to do is develop a data set that is labeled this time. So again, looking at the 4 development stages that James was just talking about, and trying to find projects that we know are at one of these 4 development stages, and then using that instead for a supervised algorithm this time. And we think that could be we hope that could be successful. Really cool. Yeah. So that's some insights into future work.
I really like too that you're emphasizing here that the peripheral contributors are important, right? Because we always tell the interns that, but this is like, no, it's really true. You can see it. It's you know, demonstrable. So that's really neat to see something like that show up as, you know, related to criteria that you use for deciding what's healthy.
Yeah, it helps me feel better about myself too. So it's great. All right. Thank you, Michael. All right, well, if that's it, thank you so much for coming. And I hope you guys learned something. And if anyone wants to contribute to this research at all, you know, be sure to let me or James know. We would love to have more hands on this project.
We had a question from Michael.
Do we?
I saw a hand raised. I might have been wrong. Might have been a goodbye. Oh, never mind.
Sweet. Thanks, Michael.
Awesome.
Thanks a lot. This is great.
Thank you, guys.